Hey everyone, how are we doing today? Hope everybody is doing well. It is a nice fall day here in my barn. So we got not too long a lecture here, a little bit shorter lecture, so let's go through that one today. So today we're going to look at higher order derivatives. And let me see, what section is this? This is 2.6. So 2.6, higher order derivatives. So we've been working with all sorts of different techniques to find different derivatives, but all we've done to this point is the first derivative. So you can actually go farther. You can go to the second derivative, the third derivative, the fourth derivative. You could take derivatives for a long, long time. So when we look at the first derivative, we should be familiar now with that notation. So the first derivative would be the f prime of x. Okay. So if we want the second derivative, its notation is going to be f with a double prime of x. Okay. And then if we do want the third derivative, that will be f triple prime of x. Now after that point, so these are the three that are most useful. So the first derivative, obviously we've already been working with that one. The second derivative and the third derivative. If for some reason you want to go farther than that, so let's say you wanted the fourth derivative, we don't use four little primes, we just write f4 of x like that. Okay, so, if that ever pops up, I just wanted, that's not raising the function to the fourth power, it's the fourth derivative of f, okay? Okay, so basically we just want to do some practice here. So let's say that I gave you the function f of x is equal to x to the fifth minus 3x squared, 3x to the fourth, plus 4x cubed minus 2x squared plus x minus 8. Okay, so just give you a big old nice long polynomial there. And let's see, they're going to ask you something like find the first three derivatives. So find first three derivatives. Now, almost always, in order to get one derivative, you have to have the derivative before it. So it's not like you can jump all the way to the third one or the fifth one or whatever. You gotta have to work your way through the process, which is nice. So if we want the first three derivatives, we're just gonna take the derivative 3 times. So we wanna make very sure that we've got our notation set so that we're telling people which derivative is which, so we're not confusing anybody. Okay, and again, we start with a nice polynomial, so we'll bring down the 5x to the fourth. Bring down the 4 will be negative 12x cubed. Bring down the 3 will be plus 12x squared minus 4x, and then a plus 1 there at the end. Okay, look good? All right, so there's our first derivative. So then if we want the second derivative, all we're going to do is just use this function right above us and take the derivative of it. So bring down the 4, we'll have 20x cubed minus 36x squared, plus 24x minus 4. Okay, right? And then we're going to go again, they want another one. So f triple prime of x is equal to, let me move it to this side. So bring down the 3, so that'll be 60x squared minus, bring down the 2, 72x plus 24. So what you kind of notice here is, as long as you have a polynomial, what really happens is the hardest part is the numbers are going to get bigger on the front, right? But the other thing I want you to notice about a polynomial is, notice how we started as an x to the fifth, and every time we take the derivative, the polynomial drops by a degree, doesn't it? So eventually, will be down to the point where the derivative will be just 0 because there won't be anything left. Okay, so that's the nice thing about polynomials, is that they cycle down like that. So that's why we start with taking the second and third derivative using a polynomial, but they don't always come to us as polynomials. So we got to be able to do this even if we don't have polynomials. So let's look at, so we'll start still not too bad, and then we'll do one more good example, and then we'll go to the nasty one. Okay, so this time they're telling us that y equals 1 over x squared. And they want us to find the fourth derivative. Now, I really honestly don't know why we'd want to do this, but they're asking us to do it, so we will do it. Now, again, wouldn't it be nice if we could just go right to the fourth, but we can't. We've got to cycle through all the others, so we've got a ways to go to get this. So if there is our function, though, first thing we want to do is get that x squared up to the top. So we're going to rewrite x to the negative 2 and just make our life that much easier. Okay, so now we're ready for the first derivative. So we bring down the negative 2, and we have x to the negative 3, right? Now, don't do anything fiddling with this to make it back into a fraction because we're still working with it. So we'll go directly to the second derivative, which will now be positive 6 x to the negative 4. Then we'll go to the third derivative. So bring down the negative 4, so we have negative 24 x to the negative 5, right? And then one more time here, y to the fourth. And you'll also notice sometimes they put the little 4 in parentheses because otherwise that really does look like y to the 4th power. So this is the fourth derivative. And this will be, let's see, bring down the 5. That's going to give us 120, or so the negative 5. And then x to the negative 6. Right, 120. And now that we're done, if we want, we can rewrite this as 120 over x to the positive 6. Okay, so don't do that in between each step, but the final step we can go, oh, it's back into a fraction, and there we've got it. Okay, so still using kind of the polynomial rules, the power rule there on the exponents. So now let's actually see one that is quite a bit bigger and uglier. Okay, so what if f of x is 2x squared plus 3 to the 3 halves power? Okay, and we're not going to go too far with this one. We just want the second derivative. So find f double prime of x. Now, this one is going to be worse because what I see is the chain rule. Do you see the chain rule there? We've got the outside function and the inside function. So we definitely have the chain rule going on here. So we'll just work our way through this. So the first step is to find the first derivative. So take the derivative of the outside, so 3 halves, leave the inside alone, 2x squared plus 3. Drop that down by 1 or 2 over 2, so that'll be 1/2. And then don't forget to multiply by the derivative of the inside, right? And the derivative of the inside would be 4x. Everybody agree? Now, do any simplification you can at this point because then, we got to do the derivative again and we do not want it to be ugly. So I'm going to cancel out, do some canceling here. Okay, and I'm going to rewrite it first as 6x and then 2x squared plus 3 to the 1/2 power. Okay, just get it a little bit better looking there, but it's not much better looking. Now, we still need another derivative, don't we? But now we're in an unfortunate situation, Okay, not that we can't handle it, but still not the most fun. In that, not only do we still have the chain rule with this, everybody's still using the chain rule, but this is multiplied on the front, so we also have the product rule. So the product rule and the chain rule, what a pain in the butt, okay? So, like I said, they get big and ugly. So if we start with the product rule, take the derivative of the first guy, which luckily is just 6, okay? Leave the whole second guy alone. 2x squared plus 3 to the 1/2. Plus, write down the first guy, 6x. And now we're going to take the derivative of the second guy. So here's the chain rule. So bring down the 1/2. Leave the inside alone. I ran myself out of space here. Sorry for trying to do it small. Drop the exponent by 1. So now we're looking at negative 1/2. And the derivative of the inside is still 4x. All right, so we took the second derivative there. It's ugly. I don't expect you to simplify this too much, but I definitely don't expect to see that crap going on. So we're gonna do a little bit of simplifying here. So we'll leave this out in front. Nothing to do with that one. Plus, and then that'll leave us a 3. So we're gonna have 12x squared, and then 2x squared plus 3 to the negative 1/2. Okay, well, we got it. Alrighty, so that's finding these higher order derivatives. So in your homework, it's really just more practice finding the derivative. So it's just like a nice review practice, except they're adding the fact that there's the second and third derivative here. But lots of power rule, lots of product rule, chain rule going on in there. So just be very careful with that. Then there comes the word problem. And in business, the second derivative has its purpose, but we're not quite ready to learn what that purpose is. We need a couple more lectures to use the second derivative in a business setting. So the only word problem that we have here today is going to be like a physics word problem, a science word problem. So we're going to look at our favorite diving person, or throwing a rock off of a roof, or that basic formula that we have seen in the past. So we're going to look at the position function. And remember, the position function is the one that looks like S. I always like to put the S of t in there. I don't know why they leave it out. Oh, purple pen, you're just about done. Here, let me get another purple pen. Okay. And then this is the negative 16t squared. Okay, so remember, we've seen this guy before. That's the idea of gravity playing on us. Let's say minus 32t plus 240. Okay, so let's say that this is the function for the position of a rock thrown off a building. Not the nicest thing to throw a rock off a building, but that's what we're doing here. So what we should be used to by this point is if I said find the velocity function. Okay, so if you're given the position function and we want the velocity function, basically what I'm asking you for there is the first derivative, right? So s prime of t, which would also equal v of t, the velocity function, is going to be equal to negative 32t minus 32. Okay. That look good to everybody? Okay. But another thing that goes along with velocity is acceleration. So think about driving your car, okay? When you drive your car, you talk about your velocity, how fast are you going in miles per hour. But when you put your foot on the gas pedal, your car speeds up, doesn't it? So you are accelerating. If you take your foot off the gas pedal, your car slows down, so you are decelerating. So as well as having velocity, something that goes along with velocity is acceleration. And acceleration is the derivative of the velocity function. Okay. Another way to say that would be to say the rate of change in velocity. Okay, the rate of change in velocity. So the rate of change in velocity, which will be acceleration, but because it's a rate of change, it makes it a derivative. So if it's the derivative of the velocity function, that means it's the second derivative of the position function. Everybody agree? So if I have the position function and I want to go all the way to acceleration, I've got to go one more step, don't I? So if we want the acceleration here, using our example there, so we're going to go s double prime of t, which would be v prime of t, which would also be acceleration of t. And fortunately, the derivative there is very easy. It's just negative 32. Okay. And then notation on this is feet per second squared. Okay, so velocity, this is just in feet per second. But once we look at the rate of change in velocity, it's feet per second squared. And the negative 32, okay, just means that we are decelerating. Okay, so we're slowing down, or wait a minute. No, we're going down. So I'm sorry. It's the position function, so it's telling us that we're going down. All right, so acceleration, okay? Second derivative of the position function. And even though we couldn't go further here, there is a third derivative when it comes to the position function, and it's called jerk, okay? And in this example, we can't do a jerk problem, but what I want you to think about is if you're driving a car, okay, so you're driving a car, we have the idea of velocity, how fast are you going? You put your foot on the gas pedal and you speed up, that's your acceleration. But then there's one more that we can attach to that. What happens if, as you're accelerating, you get hit by another car behind you? All of a sudden, your acceleration makes an instantaneous change. So that acceleration, so you're speeding up, you get hit and you jerk, okay? So imagine like pulling something real hard. There's an instantaneous rate of change there, and that jerk would be considered the third function. So if you jerk the chair out from somebody, not the third function, is the third derivative. Okay, so we're looking at the third derivative there. Okay, so what do you think? Look good? Okay. All right, so just more practice, okay? Just practice, practice, practice. And then the next lecture is a little bit uglier. Okay, so work with this one and then we'll get into the next one, okay? All right, everybody, have a good day.